Okay, previously we discussed that energy is transferred in the form of in discrete form. Okay, energy is discrete and energy is limited when it's transferred. So we will be able to get that the radiation that is emitted, okay, by a hot object. Okay, the graph between radiation against the wavelength will look like a bell shape. Okay, so now we want to see what happens if the temperature higher. What would be the difference? Okay, so look at here. As the temperature of an object rises, the object acts as a black body radiator and emits thermal radiation of all wavelengths. Okay, figure 7.2 show a graph of radiation intensity against wavelength of three types of black body at different temperature. Okay, usually every curved graph of the black body spectrum is narrower on its left, okay, which is an area with short wavelength and high frequency. With increasing temperature, the wavelength approaching maximum radiation intensity will also get shorter. Okay, so you see here, you look at this graph. So this graph of radiation intensity against the wavelength. So we have three objects here. All of these three objects is star. Okay, they are all stars. So we look at this one, the red star. So this red star have the lowest temperature, 4,000 Kelvin. Okay, so this red star that is of a lower temperature of 4,000 Kelvin, the majority of the energy go to particles that oscillate at lower wavelength. Okay, oscillate at lower, not lower wavelength, at a lower frequency. Okay, oscillate at lower frequency. So the uh, the radiation that is emitted, okay, because the temperature is lower, so that means the frequency of oscillation will also be lower. And when the frequency of oscillation is lower, then the frequency of the radiation that is emitted will also be in the lower frequency. So if the frequency is lower, that means the wavelength will be longer lah. So you see here, around here, this is red color. Red color light have a longer wavelength and longer wavelength and lower frequency. So that means most of the energy go to particles that oscillate at a lower frequency. Okay, so the radiation intensity will be the highest for red light. Okay, and if the temperature is higher, 5,270 Kelvin, then you can see that the energy, there will be more energy. So a lot of the particle can oscillate at higher frequency. When it can oscillate at higher frequency, that means it will be able to release, okay, it will be able to emit the electromagnetic radiation in almost all wavelength, okay, almost all frequency, almost all of the visible light, okay, in almost all of the color, all the different color of light. So that is why you see this star with a higher temperature will look like white color. Okay, it's white star, look like white color because all the different frequency is released. Okay, all the different frequency is released. So the combination of different color will produce white light lah. Okay, white light. While this one, the lower temperature one, most of the energy go to lower frequency, so it will look like red color. Okay, it will look like red color. And if the temperature is even more higher, 7,000 Kelvin, then a lot of the energy will be able to go to particles that oscillate at higher frequency. So you can see that the radiation intensity for blue light, violet and ultraviolet frequency will be more. Okay, will be more, but it is still the same. When the frequency increase, the particle that oscillate at a higher frequency, it will not be able to get much energy. So the number of particles that can oscillate at higher frequency will be lower. Lower number of particles that can oscillate at higher frequency. So the radiation intensity for higher frequency will be lower. Okay? So this is the same as what we discussed previously of this graph. Okay? So this is reality. Okay, this is reality. So this is the actual radiation, that is radiation intensity that can be measured from stars with different temperature. Okay, so continue. Ideas that spark the quantum physics theory. Okay, light is an electromagnetic wave. Okay, electromagnetic wave that is produced from vibration of an electric charge. So in a hot object, electrons vibrate rapidly and randomly in any direction and produce light. As the object becomes hotter, the vibration of the electron becomes more energetic, so more light will be emitted. The electron in a hot object will vibrate in a continuous frequency range. According to classical theory, electron vibrating at the same frequency should have the same energy content. The vibration frequency of the electron also has no limit. Thus, the light energy produced by the vibration of electron can reach unlimited high value. Okay, so this is what is being discussed in classical theory. Okay, in classical physics. Okay, where the logic is that if the particle can oscillate at a higher frequency, then it should be able to produce more energy. Okay, more energy will be able to be released. But this is not logical. Why? Because the frequency also can go as high as possible. As the frequency go higher and higher, it emits more and more energy. So this is not logical, because if like that, then the amount of energy that can be released by the hot object will go to infinity. That means as a frequency, that means as a frequency increase, what happens is okay, if the frequency increase, then it will become like this. That means the graph will look like this, going up and continue to go up indefinitely to infinity. So this is impossible lah. Okay, this is impossible because energy cannot be unlimited. Cannot be. There is a limited amount of energy lah. Okay. So, however, experimental results involving black body radiation are inconsistent with classical physics theory. This is where this is what we talked about just now lah. Okay, the theory is like this, going up to infinity, but reality is the amount of energy that released will go up, and then when it goes to very high frequency, it will decrease. Okay. So based on graph of radiation intensity against wavelength for black body radiation, the light intensity on the left side of the peak does not continue to increase with the increase of wave frequency as predicted by classical theory. So this controversy in the concept of light energy has sparked the theory of quantum physics. Okay, so this is what we discussed previously. Okay, in classical physics, as the frequency increase, the energy will go up and up and up. Okay, infinite going up. But in reality, it's like this, going up, and then when the frequency is very high, then it will go down. Okay. So the only way to explain this phenomena, in order to explain this graph, is through quantum theory. Because quantum theory say that the idea of Max Planck is that energy is discrete and energy is limited. So this can explain the reality, the phenomena that happen in reality. Okay, so when we go into quantum theory, okay, quantum theory, Max Planck, okay, so introduce the concept of quantum, okay, which is a discrete energy, and the electromagnetic wave emitted by black body is in discrete form, known as quantum of energy. The energy in each quantum is directly proportional to the wave frequency. We will discuss this later. Later we'll discuss this. So the intensity of the radiation is low for the high frequency wave. Okay. So this is what we observe. This is what we see in the graph. Okay, this is what it means. This one. Intensity go down for high frequency or short wavelength. Okay, we want to talk about quantum of energy. What does it mean by quantum of energy actually? Okay, the electromagnetic spectrum may be a continuous spectrum or a line spectrum. Okay, figure 7.4 and 7.5 show example of a continuous spectrum and a line spectrum. Okay, so how is it that the radiation can have a continuous spectrum and line spectrum? Usually we only see the continuous spectrum. Okay, later we will discuss that. But before that, okay, we need to look at this. What does quantum of energy means? Okay, quantum of energy is discrete energy packet and not a continuous energy. According to Max Planck and Albert Einstein's quantum theory, light energy exists in the form of an energy packet known as photon. Photons are light energy transfer in quantum of energy. So basically what quantum of energy means is that quantum of energy is a discrete amount of energy. Okay, it's a discrete amount of energy. So basically is when we have light, okay, let's say when we have bulb, okay, let's say a bulb. Okay, when the bulb light up, okay, you have light. So that means light energy is being transferred. Okay, light energy is being transferred, emitted out. So the light energy that is emitted by the electromagnetic wave, okay, is actually in small packet. Okay, small packet, discrete, very small discrete amount. So each and every discrete amount, okay, specific amount, is what we call quantum of energy. And each energy packet, okay, each energy packet is what we call photon. Okay, photon. So each packet of light energy is what we call photon. Okay, so what Max Planck found out, Max Planck and Albert Einstein. Okay, what Max Planck and Albert Einstein found out is that the relationship between photon energy and frequency of light wave is that they are directly proportional. So that means the higher the frequency of the light wave, the higher the energy quantum of a photon. Basically, it means that if the frequency of the light is higher, then that means this light, each and every photon, okay, each and every photon will have the energy inside will be higher. Okay, each energy packet, the energy that is inside the photon will be higher. Okay, if the frequency is higher lah. So that means if you have a red light, then red light have a lower frequency. So that means the photon of red light will have lower energy lah. Okay, lower amount of energy compared to let's say green light. Okay, green light. Green light have higher frequency. So that means the photon of green light will have more energy lah compared to the red light. Okay, so the relationship. Okay, so the relationship that they get that between the energy and the frequency is that they are directly proportional. Okay, they are directly proportional. So from this graph, if you look at this graph, it's very logical because if the frequency is zero, that means the particles are not oscillating. Not oscillating, then that means it is not able to release electromagnetic radiation. So if it cannot release electromagnetic radiation, that means there is no photon so energy is zero. So the higher the higher the frequency, the higher the frequency of the oscillation. Okay, so from this relationship from the graph, okay, so the graph you see just now we say that if the frequency is zero, so that means the particle is not oscillating. So that means it's not releasing any electromagnetic radiation. Okay, that means no electromagnetic radiation, so the energy content will be zero lah. Okay, no photon. So as the frequency increase, then the amount of energy will be higher lah. Okay, so the energy that is inside the photon or each individual photon will be higher. Okay, so from this graph we can create a straight line equation. So y equals to mx plus c. So y is energy, m is the gradient. So because it's a straight line, so that means the gradient must be a constant number lah. Okay, must be a constant number. So we put k lah as the constant number. So this x is the frequency, c is 0. Okay, so from this equation, this k, the constant number is this constant number. They found that this number is a very, very, very small number. Okay, it's a very small number. 6.63 times 10 power by negative 34. Okay, so the unit is joule second lah. Okay, the unit is joule second. So this constant number, this very, very, very small constant number is what we call the Planck constant. Okay, the Planck constant. So the symbol of the Planck constant is a small h. Okay, so h f like that lah. E equals to h. Okay, so we can see also that why is it that the unit is joule second is because Planck constant, okay, E equals to hf. Okay, so Planck constant will be equals to the energy over the frequency. So the unit of energy is joule, the unit of frequency is hertz, but hertz is also per second. Okay, per second. So 1 over second. So the unit of the Planck constant will be joule second. Okay.